Good day everyone, this is the Muon Physics lab. I'm going to explain the equipment that we have here. So here we have a signal generator. It could change between sine wave, square wave and such. We'll only be using the sine wave feature on this. Here we have a digital oscilloscope. You would have used this already in your year 1 labs. Here we have the electronics box. So this has the amplifier and the discriminator, and it has an audio signal to see when we detect muons also. This is our scintillator. So this is what actually detects the muons. When it detects the muons, it sends the output to the electronics box. It also has a pulsar. So it's a LED that emits a pulse of light. So basically it emits two signals that are very close to each other. That's just for our initial setup. When we're actually doing the experiment, we'll take that off. Here we have our program that we're going to use to record the data is open, but right now we don't have any data on it because this is just the initial setup. So we could get ready to start. So inside our scintillator, we have a photomultiplier tube or a PMT, and we have a crystal. So what happens in our scintillator is that a muon is incident on the scintillator and it loses energy while passing through the scintillator. And when it loses energy, the energy is transferred from the muon into the electrons of the scintillator crystal. And the electrons are excited. And when the electrons are excited, after some time they decay. So they emit a photon. That photon is detected by the photomultiplier tube. And the photomultiplier tube converts that signal from the photon into an electrical signal. And that signal is sent into our electronics box. And then from the electronics box to the amplifier and discriminator output you can see on the scope, and it's sent directly to the software as well. So now we have the experiment set up as in part 1 of the lab manual. So the signal generator is set to 100 kilohertz and an amplitude of 100 millivolts. The output from the signal generator is sent to the input of the electronics box, and the amplifier output of the electronics box is sent to the oscilloscope. And on the oscilloscope we could see the sine wave, but an amplified sine wave that's amplified by electronics box. So we know that the output of the signal generator was 100 millivolts. We're going to measure the output of the amplifier on the oscilloscope, and by doing that we could find the gain of the amplifier. So right now we are seeing that the oscilloscope has a peak-to-peak voltage of 1 volt. So that is approximately a gain of 10. And if we look in our lab manual, we can see that the actual gain is 21 times this value. We can see that as I increase the frequency, the wavelength is decreasing, which is the distance between two crests or two troughs. But we also see that the amplitude is also decreasing. We see that as I decrease the frequency, the wavelength is increasing, so the distance between troughs are increasing, and we also see that the amplitude is increasing. To quantify this change in gain with frequency, I'm going to set the signal generator to 125 kilohertz. Approximately 125, and then we're going to measure the gain again. And what we have to do is we're repeating this for different frequencies. So it goes from frequencies from 100 kilohertz to 700 kilohertz in steps of 25 kilohertz. And then we'll find the gain as a function of frequency. And that's it for part 1. So for the second part of the experiment, we're going to measure the saturation voltage of the amplifier. That's basically the highest amplitude that we'll get from the amplifier that will keep the signal that was input into it. So basically anything beyond the saturation voltage, you'll get a flat line basically. So how I'm going to do that is by changing the amplitude of the signal generator, and then we'll see the difference on the oscilloscope. I'm increasing it right now, and while doing this we'll have to keep changing the scale of y-axis, which is the voltage, the amplitude, so we could keep seeing the sine wave signal. So if you look carefully, as I increase the amplitude of the signal generator, the bottom of the sine wave is getting flat. And as I keep increasing it, the width of the flat part gets larger and larger. It's no longer a proper sine wave. And we can see it's properly flat here. So that is basically saturation. Now we see that the top of the sine wave is also saturated. So to find the saturation voltage, we're going to find the maximum amplitude of the sine wave just before the crest and the trough of the sine wave get flat. So I'm going to reduce the amplitude of the signal generator. And I'll change this horizontal axis scale so you can get a better view. So we can see that it's somewhere around here, which is 2.60 volts that we're getting the saturation of the amplifier. Because if I increase it slightly, we can see that the bottom has already started getting saturated. So that's it for part 2. Now we have the apparatus set up as in part 3 of the lab manual. So in part 2, we took the output from the amplifier and sent it to the oscilloscope. In part 3, we're taking the output from the discriminator and sending it to the oscilloscope. What you would notice is that there's a termination here on the amplifier. I also have one here in my hand. These are 50 ohm terminations. So we have to keep these connected to the amplifier and the discriminator so that we get a proper signal on the oscilloscope. These cables also have the 50 ohm, well, it's not a termination, there's a 50 ohm resistor built into the wiring of the cable so that we get proper signals on the oscilloscope. Otherwise, we might get some kind of distortion. So now we're going to see the effect of changing the threshold of the discriminator. We're visualizing it on the oscilloscope. So right now I've set the threshold to the minimum value and I'm going to increase. What we could see on the oscilloscope is something like a square wave, right? We have a low signal, then we have a high signal, it's gone back to low. We're using a 100 kilohertz signal from the signal generator, so that's why we get a repetitive signal. So now I'm going to increase the threshold value and you could observe the difference on the oscilloscope. So, can anyone tell me what difference you have seen on the signal on the oscilloscope? What we have seen is that the peak of the square wave has widened, but the trough, the lower part, has gotten smaller. So, the value of the output of the discriminator, as the threshold increases, it has a longer time with a high voltage and a shorter time at a low voltage, as we can see here. Alright, so now I'm going to use the software that we're going to be using for this lab. So here we have the Muon software. I'll double click it to open. And what we have to do is we have to configure the software to recognize the equipment. So to do that, we zoom into configure. So we double click on configure. Then we go to select port COM4. The output from the electronics box is connected to the COM4 of this computer, so that's why we choose COM4. If you had a different setup at home, you might have used 1, 2, or 3. We'll keep the decay time on the histogram scale. That's basically what we're seeing here. We'll keep it at 20 seconds and we'll keep the bit number at 20. We press save and exit to save those settings. What we see here on this software, we're seeing the rate meter. When we start recording, we'll see lines popping up on this rate meter representing different detections. We also have here the lapse time from when we start the measurement, the number of muons that we detect, the muon rate also, the decays and the decay rate. This diagram that we have here, this is the number of muon decays in a histogram format. When we start taking measurements, we'll see the histogram being populated. So right now, the apparatus is set up to do part 4 of the lab manual. So what I'm going to do is I'll click start. And we can see here, there's a point that's being increased at 0 microseconds bin. We could see here in the rate meter though, that there are a number of events being detected. This is not actually muon events, but this is the pulsar on the scintillator. We're detecting pulses from the pulsar here. And we can see here the time is being changed. The number of muons is actually the number of pulses from the pulsar that we're detecting. The rate is here constant. And the decay rate, right now, typically the pulses are so close together that it appears to be one pulse, as we'll see soon. And the muon decay rate is basically 0 because what we're only seeing is one pulse. So it does not appear to be a decay,
meaning that it does not appear to be two separate events.
So here I have the setup as in part 4 of the lab manual. The PMT output from the scintillator tube is input into the electronics box, and the pulse output of the scintillator tube is incident onto the scope. So we have a knob here on the scintillator that allows us to adjust the distance between two pulses. So what we're going to do in this experiment is we're going to adjust the time interval between the pulses, and we'll see how it appears on our oscilloscope, and we'll see how it appears on the software as well. So right now the knob here is set to 0. So basically there's no time interval between the pulses, and we're basically seeing one pulse. There's a small error, as we see a small black part of the pulse. That's basically like 0 error in our apparatus. What we're going to do is we're going to change the pulse, and we'll compare the reading on the scope to the reading on our software, and we'll plot a graph. So we'll start taking our readings from 1 since we have this small 0 error here. Okay, so now we have the pulsar. I've changed the value of the pulsar on the scintillator to a value, and that we're going to measure that value on the oscilloscope. Right now the oscilloscope is set to 1 microsecond per division. So we could see that the distance between both pulses is 1 division. So therefore the time difference between both pulses is 1 microsecond. Now we'll head over to the software and see what the software is showing. So now I'm going to start taking the values from the software, and we could see that the value is at 1 microsecond. So right now the oscilloscope and the software have the same value. Now I've adjusted the pulse output to 3 microseconds. As you can see here, the scale is still 1 microsecond per division, but now there are 3 divisions between the vertical lines. So therefore, we have 3 microseconds between the pulses of the pulsar. And now we'll go over to the software and we'll see what we get on the software. On the software, we could see that we're also seeing 3 microseconds for the decay time. That is basically the time between the pulses of the pulsar. So for part C of this experiment, what we're going to do is we're going to adjust the time difference between the pulses, and we're going to see the point at which the software no longer picks this up. So I'm going to start I'm going to start the recording on the software, and we could see right now it's detecting the difference between the pulses to be 0 microseconds, and we're seeing a count on the rate meter. Now I'm going to increase the time between the pulses, and we could see the increase on the histogram on the software. And notice we're still seeing a count on the rate meter as well.
Remember, the pulsar represents muon decays. So the first pulse represents when a muon slows within the detector, and the second pulse represents if a muon decayed within the detector. So by changing the time interval between the pulses, we're simulating different muon time decays.
And as you could notice, we're coming to the end of the graph, the histogram. We're still seeing a count on the rate meter, But what I'm going to try to find is the position at which there's no counts on the rate meter anymore. So you can see right there, I've adjusted the pulsar so that we see no counts on the rate meter. So how do we measure this? We can't use the software, we can't use the histogram to find the time between the pulses because it's not being detected on the software. So tell me, how can we find this? So the answer to that question is to use the oscilloscope. We can see the linearity of the results between the software and the oscilloscope as we plotted in the graph previously. We can measure the time between the pulses on the oscilloscope. So right now it's set to 5 microseconds per division, and we have 4 2/5 of a division. So we can measure the time difference between the pulses, which can no longer be recorded on the software. Any larger time difference also will not be recorded. So in part 5, what we're going to do is we're going to find the ideal setting of the discriminator threshold. We have the output of the photomultiplier tube going into the input of the electronics box, and we've turned off the pulsar that we were using in the previous experiments. We have the high voltage adjust on the photomultiplier tube set to 10 volts if we measure it with the multimeter, but the value that we read on the multimeter is 100 times less than the actual value, so it's actually set to 1000 volts. So now we're going to adjust the discriminator setting so that we get the maximum muon concrete. So how we're going to do that is we're using the knob on the discriminator. We're going to read the values on the voltmeter that's connected to the electronics box to get the discriminator voltage, and we're going to look at the concrete on the software. So I'm going to click start on the software. And right now at 0 volts on the discriminator, we're not getting any rates on the rate meter, and we're not getting any muon decays or muon rates. So now I'm going to adjust the discriminator value, and we're going to look for the maximum value of the muon rate. So you can see right now the discriminator is at 0.07 volts, and we're starting to get some values on the rate meter, and we're getting a muon rate that's varying between 10 and 20. So I'm going to keep adjusting. And we can see that when I'm increasing the voltage, the muon rate is dropping. So I'm doing this a little bit quickly. If you were actually doing it in the lab, you would have to take your time and do it. But this is just for demonstration purposes for the video. But your results that you would get would be when it's actually done properly. You can see I've increased to about 300 millivolts, and the muon rate is very, very low. So I'm going to go back to a lower discriminator voltage, and we will see that the muon rate is increasing. So it will take a little bit of time to find the ideal values, and that will be provided to you at the end of the video. So now I've moved the voltmeter from the electronics box to the scintillator tube. And now we're going to do the same thing that we did with the discriminator setting. We're going to adjust the high voltage adjust on the scintillator tube, and we're going to find the ideal concrete on the software. So let's start. I'm turning the voltage down to a very low voltage. Remember, the output from the scintillator tube is 100 times less than the actual voltage in the scintillator. So this, what we're seeing here, 1.25 volts is equal to 125 volts within the PMT. So let me increase. We can see that there's no rate detected on the screen, right? And I'm increasing. Even 4 volts on the voltmeter, I'm not getting anything. 5, 6 volts, still nothing. Even up to 7 volts, we're not getting any reading. 8 volts, we still have nothing. And we see a little more than 8 volts, we start to get a muon rate, and we see our rate meter being populated. And while I increase the voltage, you can see that the rate is increasing slightly. And it's very slow increase. And again, as I said with the discriminator setting, this is just a little bit rushed, just to show you what to do if you're actually doing it in the lab. Well, if you were doing it in the lab though, you would have to take your time and spend more time to see the actual differences properly. And we can see the rate is still increasing as I increase the voltage. So right now the voltmeter is maxed out at 10.65. So our maximum value is slightly less than that, our maximum concrete. So when I actually do it properly to get the values, I'll give you that at the end of the lab for your results. So that's it for part 6. So now we have the apparatus set up as in part 7 of the experiment. We have the output of the amplifier going to the oscilloscope. We already did this with the pulsar, but now we're actually going to observe the muon rate and how that affects our output from the amplifier on the scope. So right now we've hit the run stop button on the oscilloscope so we can get a clear picture of what has happened at one instant. So we can see there's some noise in the signal here at the bottom, but you see that there's a peak in the oscilloscope, and that peak represents the pulse of light that was generated when a muon either decayed within the apparatus or when a muon slowed down within the scintillator. So this is our signal, and we can see it kind of resembles the signal that we got from the pulsar, except if we look here carefully, we can see that the magnitude is about 20 millivolts after coming through the amplifier. So that's why we can see the noise now. And you notice we would not have seen noise with the pulsar, because the pulsar would have given a larger voltage. So relative to the noise, it would have been large. I'm going to click run stop again so that we can actually see how it's happening in real time, right? This is the signal given by one muon. But remember, there are multiple muons coming in, so we'd get multiple signals. So in real time, we can see that the peaks are just coming and going. That's every time a muon is either detected or a muon is decayed. The amplitude of this signal is very small. And remember, the amplifier is amplifying the signal. So that's to show how small the actual signal that we pick up from the scintillator because of muon decay or muon slowing in the apparatus is.
The amplitude of what we're seeing also is varying. That is because of the different amounts of energy being deposited by either slowing down or decay.
The second part of this part, we're going to connect the discriminator output to the amplifier, and to the oscilloscope, and we'll see what happens. So I'm going to connect it in channel 2, so we can see both the amplifier output and the discriminator output. So now I've connected the discriminator to the oscilloscope in channel 2 of the oscilloscope, and we can see that is the bottom line here with the small pulse, and the amplifier is the top signal that we see on the oscilloscope. When we see a muon, when we detect a muon through the amplifier, we see a increase in voltage, but with the discriminator, when a muon is detected, we see a decrease in the voltage, as we could observe here on the amplifier. And you can see that when the amplitude of the amplifier decreases, the drop in the discriminator voltage also decreases at the same time. And when the amplitude of the amplifier increases, the drop in the voltage of the discriminator again at the same time increases. So you can see there's a correlation between the amplifier signal and the discriminator output at the settings we obtained in part 5 and part 6 of this lab manual. Now, as a side note, I'm going to show you a feature of the electronics box. So you can see on the electronics box here there's an audio button, and for all of the experiment we had it set to off, right? But I'm going to turn it on for now, and you can hear a signal that sounds like noise, right? I'm just going to put the mic closer so you can hear it a little bit better. It basically sounds like, okay, I took it off. So it basically sounds
like noise on a TV connected to the antenna where there's no channel, or like on the radio when you're driving through the northern range.
This is basically background that we get if we did not want to detect muons. In this experiment, we want to detect muons, so we want to hear this noise. But like, if we did not want to do it in other particle physics experiments, this is cosmic radiation. If we don't want to detect muons, say we want to detect dark matter or neutrinos, the muons would be a source of background noise, and it's something we want to eliminate. So there are different methods in the different experiments to eliminate background noise. So this is just a side note just to show how muons can affect experiments. As we did in 5, 6, and 7, what we did, we adjusted the threshold value of the discriminator, and we also adjusted the high voltage output of the PMT to obtain ideal settings for muon detection, right? But if we wanted to determine the signal from something else, we might have different settings on these so that we would get a low detection rate of muons, but we might get a higher detection rate of some other particle. So when we adjusted this value now, we're detecting mostly muons and maybe less of other particles. So that's just the setup for this particular experiment. So now we're doing part 8 of this experiment, which is basically the longest part of this experiment. What we're going to do is we're going to start detecting muons and find the decay rate using the software, but we have to let this run for a very long time, approximately 2 hours. So that's longer than the lab's going to be online. So what we'll do is we'll leave it, let it run. We'll come back after when it's close to the end and we'll show how it's progressed, and then we'll discuss that afterwards. So we'll cut out just standing up here and waiting, as you would have done if you were doing the experiment online. I'm sorry, not online, in person. So I'll configure it again and click start, and we've kept the settings the same as we did it in part 6 and 7. So now what we're doing is we're just going to let this run. We can see we're still getting a nice rate on our rate meter. We're getting a decent muon count rate, and our decay histogram is being populated already. So we'll just let this run for 2 hours and we'll be back then. Okay, so now after 2.5 hours, as you can see the elapsed time here, 2 hours and 30 minutes has passed. We're getting this graph for the muon decay. So we think that enough time has passed and we're getting a decent graph. We're going to stop taking data and we'll get our calculations and results. I'm going to make the fit for our curve. So I'll click pause, and now we've stopped taking measurements. So I'm going to click fit, and they ask for a password. So I'll type in our password, which is muon. Click submit, and we've got an exponential fit to our data. So we can see that here we have something with tau. So tau is our muon lifetime that we got from this fit, and chi-squared and the degrees of freedom are given here to be 15.0 and 18. So these are some statistical values which we'll talk about now. We've basically done everything that we have to do for our lab session in lab. So now everything would be calculations that we can do